Okay, welcome everyone. So today we have a very special webinar because it's also our 10th anniversary. We complete 10 years today, and it's a pleasure and an honor that Professor Ken Ono has kindly agreed to give the talk today. So before going into the talk, let me very briefly introduce Professor Ono. He needs no introduction to this audience because he is quite a well-known number theorist and has a strong connection with India. But for some of you who might not know him, let me introduce Professor Ono. Professor Ono is at present the Thomas Jefferson Professor of Mathematics at the University of Virginia. He is one of the most prominent living number theorists and is widely known for his work in number theory, especially his work related to partitions of integers and modular forms. He received his BA from the University of Chicago and his MA and PhD from the University of California, Los Angeles. Before moving to the University of Virginia, he has held positions at various institutes, including the University of Illinois at Urbana-Champaign, the Institute for Advanced Study, Penn State University, and Emory University. So he has been or is an editor of several important mathematical journals, including the International Journal of Number Theory, Proceedings of the American Mathematical Society, and the RAMANUJAN Journal. Professor Ono has also sat on various award committees and has served on the boards of various organizations, including very recently as the Vice President of the American Mathematical Society. It's our honor to have Professor Ono with us, and today he's going to speak about the Riemann hypothesis. Professor Ono, up to you, over to you.
All right, great. Thank you very much, Manjul. I'm delighted to be with all of you this morning. It has been a challenging year with COVID, and so I'm not accustomed to not traveling at all. And so these Zoom meetings certainly go a long way to helping us stay connected as a scientific community. Great. So I'd like to give a lecture today on the Riemann hypothesis. As you can see, I'm using a version of this lecture that I gave before I moved to Virginia a little over 1 year ago. I was a professor at Emory University, but not very much has changed in the last year. The Riemann hypothesis is very much an open problem. So I would like to have fun with this lecture. And the point of this lecture is to explain what the inspiration is for the Riemann hypothesis, why it matters, and time permitting, I'll give some indication of some of the things that we've proven about the Riemann hypothesis, although to be absolutely clear, I think a proof is very far off. I hope I am wrong, but I think that's likely the case. So as I said, I'd like to begin with a little bit of fun. And on this slide, which is titled, "It is hard to win $1 million," I just want to indicate that you can win $1 million if you know how to answer certain questions. In fact, the famous television show, Who Wants to Be a Millionaire, is one way in which you could win $1 million by answering questions. But as you can see on the slide, the questions can be difficult. As you can see, which of the following is the largest? A peanut, the moon, a kettle, or an elephant? And well, just like the Riemann hypothesis, answering some questions can be quite difficult. It can be really hard to win $1 million in terms of problems that come with a bounty. And of course, what I am thinking of are the Clay Millennium Prize problems that were assembled at the turn of the century, 20th to the 21st century. And the Riemann hypothesis is one of the 7 problems that was highlighted as the difficult problems that should inspire mathematicians of the present day. Of these 7, only one has been solved, Poincare conjecture, quite famously by Grigory Perelman, but the others remain open, and I think they continue to drive quite a bit of modern research. So this lecture is, what is the Riemann hypothesis, what inspires it, and why it matters. Before I get to any of that content, I really have to begin by telling you about the romantic story behind the Riemann hypothesis. And to begin, let me just tell you about how certain famous mathematical historical figures viewed the Riemann hypothesis. So I'd like to tell you about G.H. Hardy, who quite famously collaborated with Ramanujan. Hardy, if you don't know, was in his day, perhaps the most influential and powerful analytic number theorist. He was a professor at Cambridge, England. But on top of his mathematical prowess, he was a very curious and colorful individual. He was very arrogant. He had very few friends. And he was very well known for writing criticisms and book reviews for other scholars of the day. And in particular, he was so arrogant and he thought so highly of himself. As an atheist, he thought, well, if God does happen to exist, well, maybe he is about at my level, so I might as well have a personal feud with God, although I don't think he exists. Now, what's very interesting about that, and what that has to do with the Riemann hypothesis, is a very famous postcard that Hardy sent to his friend Harold Bohr. And on a trip that he took to Denmark, before he departed, he sent a postcard to his friend, and the postcard only had the two sentences: "Have proof of RH. Postcard too short for proof." All right, so this is Hardy having fun with his friend Harold Bohr. And what was Hardy thinking? Hardy was thinking that God would not let the boat sink on the return and give him, Hardy, the same fame that Fermat had achieved with Fermat's last theorem. Point being that Fermat claimed to have a beautiful proof for Fermat's last theorem, but his copy of Diophantus's book on arithmetic, the margin just wasn't large enough to fit his proof. Continuing with the history and in the spirit of prize problems, I can tell you about David Hilbert. Hilbert was a very influential German mathematician, and at the turn of the previous century, 19th to the 20th century, Hilbert famously assembled a list of about 24 mathematics problems. He released this list about the time of the first International Congress of Mathematicians. Once Hilbert was asked about the Riemann hypothesis, and his famous quote in response is this: "If I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven?" Well, what's interesting about that is that it clearly indicates that Hilbert was mathematician through and through. Although I am a mathematician, I have to say that my first question would not be whether or not the Riemann hypothesis has been proven. My first question would be, are there any people around to talk to? But maybe my second or third question would be, has the Riemann hypothesis been proven? So what is the Riemann hypothesis? Well, this slide is meant to be intentionally opaque. The Riemann hypothesis was formulated in the mid-1850s. It was published in Riemann's only paper in number theory in 1859. Here is an image of Riemann. And the Riemann hypothesis is just this bizarre statement: the non-trivial zeros of zeta of S have real part equal to 1/2. All right, well, as stated, I probably have a long way to go to convince you that this statement deserves a $1 million bounty. And that is essentially the goal of today's lecture. So the question we want to answer is, what in the world does this conjecture mean? And on top of that, why does it matter? So to understand why the Riemann hypothesis matters, I don't have to introduce you to any technical objects. That's one of the wonderful things about number theory. To explain the meaning and importance of the Riemann hypothesis, I only require that you know about prime numbers. So a prime number is a natural number exceeding 1 that have no positive divisors other than 1 in itself. And we care about the primes as a prototype for all multiplicative structure in mathematics because of the fundamental theorem of arithmetic. The fundamental theorem of arithmetic asserts that every positive integer factors uniquely as a product of primes, uniquely up to reordering, right? 2 times 3 and 3 times 2 certainly shouldn't be considered as different factorizations of the number 6. And so with pencil and paper, you would have no difficulty listing the first few prime numbers. And if you were to do that, you'd begin with the list 2, 3, 5, 7, so on and so forth. And despite the fact that in theory, it is not very difficult to test whether any given number is prime, it turns out that there are many open, difficult problems about these numbers. So this allows me to recite for you one of my favorite quotes about the prime numbers by my friend Don Zagier, and it's related to this phrase: the primes are ornery. I hope that's a word that you know. Ornery is a kind of inconvenient, is a kind of inconvenience, and I think my friend Don does a very beautiful job of describing in a paradoxical way what's mysterious about these numbers. Don says, primes grow like weeds, seeming to obey no other law than that of chance. Nobody can predict where the next one will sprout. Okay, that seems pretty clear. Primes grow like weeds. I don't personally want weeds, I want primes, so swap out weeds by something else. Flowers. Primes grow like flowers, seeming to obey no other law than that of chance. Nobody can predict where the next one will sprout. But then Don goes on to say that primes are even more astounding, for they exhibit stunning regularity. There are laws governing their behavior, and they obey these laws with almost military precision. You must be wondering, how is it possible that the two parts of this quote could be speaking of the same numbers, the primes? How can they seem to obey nothing but chance, but on the other hand, follow other rules by what could be described as military precision? All right, by the time I'm done with this lecture, I think you'll get a sense of what that means. And what I'd like to do is begin with some very well-known features about the primes that could mislead us into thinking that the primes are easy to study. So let me begin with the sieve of Eratosthenes. The sieve of Eratosthenes is just a simple procedure. It's an algorithm. It's a step-by-step process that you can teach a computer that allows you to list all the prime numbers up to some given bound. And that's the key, some given bound. I want to list all the prime numbers up to some number X. How would I go about doing that? And that's what the sieve of Eratosthenes is about. To illustrate the sieve of Eratosthenes, I only need to show you this picture. And so what this picture illustrates is the process of trying to find all the prime numbers up to the number 50. So the given bound in this picture is 50. How would we find all the primes up to 50? Well, we would begin by crossing out the number 1, because we know that that is not prime. And so after crossing out the 1, the very next number that's left, the number 2, must be prime. But after we identify the prime number 2, let's systematically strike out all the even numbers, because they cannot be prime. They are all even. After we have X'd out the number 50 and all the even numbers after 2 up to 50, the very next number that has not yet been crossed out, the number 3, has no choice but to be prime. And then we systematically X out the multiples of 3 after 3, the 6, the 9, the 12, all the way up to 48. And after we've done that, what we know is the very next number that hasn't yet been crossed out, the number 5, must be prime. Repeating in this way, we cross out the multiples of 5 beginning at 10. We then find the next number that hasn't been crossed out is 7. So we X out the multiples of 7. After we cross out 49, we will then find all of these numbers that are boxed in. And it turns out that they all have to be prime. Why do we know that they all have to be prime? Well, any number up to 50, which is not prime, has to be divisible by an integer that is no larger than its square root, right? If you multiply two numbers together, right, the largest the divisors could be would be the square root. And because the square root of 50 is not as large as 8, the moment we've struck out all the multiples of 7, all of the remaining numbers that have survived have no choice but to be prime. And so this is a very efficient, rapid way of listing the prime numbers. However, it's not a very good device if you want to prove theorems about the whole set of prime numbers. And that is the spirit of the question that the Riemann hypothesis is aiming to address. So the first question you might ask, and this theorem predates the sieve of Eratosthenes, is this beautiful theorem of Euclid. And Euclid answered the question, how many prime numbers are there? And he says that there are infinitely many primes. So let me remind you this proof. My guess is most of you know it. It's very simple. There are a number of ways of describing it, but you could describe it in this way. Suppose you start with and identify the first R prime numbers, P1 through PR. So the first prime is 2, the second prime is 3, so on and so forth. So you list the first R prime numbers. What you can do is take those first R prime numbers, multiply them together and add 1, you get a much, much larger number called capital P. But by the fundamental theorem of arithmetic, capital P must have a factorization into primes, because every integer greater than 1 has a factorization into primes. And so it turns out that every prime number P that divides this capital P cannot be any one of the R prime numbers you started with, because capital P leaves a remainder of 1 when you divide out by any of the first R primes. Therefore, in this way, we know that starting with any R primes, we can find an R plus first prime, and you can repeat this indefinitely, and so there must be infinitely many primes. Now, unfortunately, this theorem says that there are infinitely many primes, but it gives very little indication as to how infinite this set is. Up to 1 million, how many primes do you expect to get? Up to 10 to the 7th, how many primes do you expect to get? Up to 10 to the 10th, how many primes should there be? So if you're interested in counting problems, knowing that some set is infinite isn't very reassuring, because you'd like to know how far apart these infinitely many primes can be. How are they distributed? Okay, so that is what I'd like to address now. So it turns out that some of the ideas that go into the construction and motivation for the Riemann hypothesis have their origin in much more elementary works of Euler, in his works on the phi function and elementary multiplicative number theory. So the geometric series is what we want to start with. Suppose that R is any real number, an absolute value not exceeding 1. The geometric series in R can be written in a more compact form as 1 divided by 1 minus R. 1 plus R squared off to infinity can be written in a more compact way as 1 divided by 1 minus R. And you might ask, what is the utility in this simple formula? Well, the utility is that you can assemble very strange infinite series expressions quite simply from the prime numbers using this identity. So here are 4 identities that I want to show you, and let's just discuss them one by one. Starting with the prime number 2, you can write down the geometric series in 1/2. 1 divided by 1 minus 1/2 is the geometric series in 1/2. And it happens to equal and simplify to be the number 2. However, if you start with the first 2 primes, 2 and 3, here we multiply together the compact formula for the geometric series in 1/2 and 1/3. And if you were to formally multiply out those 2 geometric series, you get this infinite sum, which is the sum of the reciprocals of the positive integers that are not divisible by any primes exceeding 3. So this is a larger number than 2, and if you multiply it out and simplify, you get the number 3. Similarly, if you start with the first 3 primes, 2, 3, and 5, and write down the geometric series and their reciprocals, what you're doing is you're summing up the reciprocals of the positive integers that aren't divisible by any primes larger than 5, and that's a bigger number, 15/4. And again, now if you repeat this again with the 4th prime, if you sum the reciprocals of the integers without prime factors exceeding 7, you get an even larger number called 35/8. And so the idea is you get a sequence of increasing numbers, 2 up to 3, up to 15/4, up to 35/8, which are in correspondence with the next primes via these geometric series, or what turn out to be the sums of products of geometric series, which is really like summing the reciprocals of the integers with a bounded number bounded prime factors in terms of size. And what Riemann's idea is if you could somehow emulate and make a proper analysis out of studying the reciprocals of integers, you certainly must have some insight into the distribution of primes building on these kinds of formulas. Well, just by the fundamental theorem of arithmetic, if we take those examples to infinity using all the primes, we get a formal power series identity that says the sum of the reciprocals of the powers of the positive integers n, summation 1 over n to the s, formally is the product over all primes p of 1 divided by 1 minus 1 over p to the s. As a formal series, this makes sense for all parameters s, for all values of s as a formal parameter. As an object in analysis, it doesn't make sense for all values of s, but for real numbers s greater than 1, this certainly is well defined as an identity of numbers. So for example, Euler already made use of this observation. If you plug s equals 2 into the left-hand side, you're summing up the reciprocals of the perfect squares. And what it turns out that you get, either from complex analysis or from identities arising from trigonometry, you can show that the sum of the reciprocals of the perfect squares adds up to pi squared over 6. This is actually very interesting. If you analyze the right-hand side here, where s equals 2, if you reciprocate that, you'll be multiplying out numbers like 1 minus 1/4, with 1 minus 1/9, with 1 minus 1/25. That's what you'd be multiplying out when s is 2. And if you think about that for a moment, just by elementary probability, that would then tell you that the reciprocal of pi squared over 6, in other words, 6 over pi squared, would represent the probability that an integer selected at random is not divisible by a square. And it's true. The square free numbers constitute about 60% of the integers, which is the reciprocal over 6 over pi squared. So already this identity has many applications just in the study of factorizations of numbers. But we're interested in the primes, and these are the numbers that don't factor at all. So let's see if this idea could be put to good use without having the Riemann hypothesis. So Euclid proved that there are infinitely many primes without giving an explicit lower bound. Let me show how we can get a better theorem, still not a great theorem, but an effective theorem by using Euler's ideas and just elementary calculus. So throughout, let's let pi of n denote the number of primes up to n. So when n is 10, the numbers up to the primes that you encounter on the way to 10 are just 2, 3, 5, and 7. So pi of 10 is 4 because there's 4 primes up to 10. And let's just prove this elementary inequality, that a number of primes up to n is at least as large as -1 plus the natural log of n. The natural log of n goes to infinity. And so this would be another proof that there are infinitely many primes. It turns out that this lower bound is very poor, but as you'll see, I will get this lower bound without hardly even trying. So to prove this theorem, as we did before, let's list the prime numbers in order. P1 equals 2, the second prime P2 is 3, and the third prime P3 is 5. So let PR be the rth prime. 2 is bigger than that index 1, 3 is 1 larger than the index 2, 5 is larger than the index 3. And so just without trying, I know that the jth prime is at least as large as j plus 1. And in fact, it will only take you a moment's thought that I can make pj be much larger than j plus 1 grows if I wanted to use the sieve of Eratosthenes, right? The reason why P3 is 5 is because 4 is not prime. And every time you don't encounter a prime number, counting up in the integers, the distance between Pj and the index j plus 1 grows. But let's not even worry about that. Let's not even try. So without even trying, this elementary observation will allow me to conclude this theorem. And all I need is calculus to get that. So from elementary calculus, I know that the natural log of n is the definite integral of 1 over x from 1 to n. And from elementary calculus, you can estimate these definite integrals by means of Riemann sums. So I will assume that m is some positive integer, and I will write down a Riemann sum using the left endpoint rule, and I'm going to add up the areas of each of these rectangles and compare them with the natural log of n. Because each of these rectangles lies strictly above the graph y equals 1 over x, this will tell me that the Riemann sum is larger than the natural log of n. So for free, I know that the natural log of n is less than 1 plus a half plus 1/3 all the way up through plus 1 over n, right? This has area 1. Since this is 1 over x, this is area 1/2. This has area 1/3, so on and so forth. Now, to make the connection to counting primes, I'm going to declare k to be the symbol that represents pi of n. So there'll be k primes up to pi of n, and I want to figure out how to access the symbol k from calculus. All right, well, by the Euler product, I know that the natural log of n must be less than the product of 1 over 1 minus 1 over pj, where the pj walk through the first k primes. Why is that? By what we described above, this product of geometric series can be rewritten as the sum of the reciprocals of the positive integers that are never divisible by a prime larger than the kth prime. And by hypothesis, the kth prime is the largest prime that you need to factorize any of these denominators. This series is much larger than this series because indeed, this has infinitely many terms. It just so happens to begin with these first n terms. Now, just using the fact that the jth prime is at least j plus 1, using the fact that the jth prime is at least j plus 1, I can further bound these in each of these individual geometric series without locating the first primes p1 through pk. So in this way, I find that the natural log of n is less than 1 plus 1 over j, where j walks from 1 to k. I get a common denominator of j, and that's just the product of j plus 1 over j, as j varies from 1 to k. So all I did was use Euler's idea and the statement that the jth prime is always at least as large as j plus 1. If you actually multiply out what this means, we're multiplying out a telescoping series. The telescoping product is 2 over 1 times 3 over 2 to the last term, which is k plus 1 over k. Literally everything cancels except the last numerator, and I find that the natural log of n is less than k plus 1. But what was k? K was the symbol that I declared to represent pi of n, and so lo and behold, what have I shown? I've shown pi of n is at least as large as the natural log of n minus 1. All right, so I didn't try. Now, this proof is more of a mouthful than Euclid's proof. Euclid's proof is the stuff of art. But if you really want to know where the prime numbers are, this little elementary proof using Euler's idea and elementary calculus and this elementary inequality already shows that with a little bit of effort, you can get a better theorem. Well, this is the situation that Riemann inherited after having studied Gauss. Gauss, as a schoolboy, was interested in counting the prime numbers, and he was basically interested in inventing the entire field of number theory. And as a young boy, he calculated these numbers, pi of n, and what he would have assembled in his own handwriting would have been a table like this. He didn't get these numbers, but he assembled tables including values of pi of x. So for the powers of 10, there are 25 primes up to 100. There are 168 primes up to 1,000. And there are a little over 5.7 million primes up to 10 to the 8th. And what Gauss recognized is that the actual values of the pi function seem to be in correspondence with this strange transcendental function, x divided by the natural log of x. And so if you were to divide this right-hand column into the left-hand column, you'll discover that you get these real numbers that seem to be converging to the number 1. And that was Gauss's famous conjecture. He said that if you define lie of x to be the integral from 2 to x of dt over log t, the logarithmic integral, he conjectured that pi of x would be asymptotic to lie of x, which happens to be asymptotic to x over log x. The first term in the expansion of lie of x is this. That's the main term. And this was a very famous open problem almost as soon as Gauss formulated it. And this is the problem that Riemann wanted to solve. In his 1-page paper on number theory, his 8-page paper in number theory, published in 1859, Riemann made use of this identity as we've used, pardon me. And he defined the Riemann zeta function. He determined many of its properties, and he posed the Riemann hypothesis, all for the purpose of identifying a strategy that would prove Gauss's conjecture. And he did all of these. So what are the theorems that are in this paper? Well, he defined zeta of s for complex numbers with real part bigger than 1 to be the series expansion that Euler found, summation 1 over n to the s, where n walks over all the positive integers. So the function he defined agrees with Euler's identity for those values, s, for which the series is absolutely convergent. But Riemann found a way to extend this series, so it defines an analytic function on the entire complex plane. This complex process is called the process of analytic continuation. What it means to be an analytic function means it's a continuously differentiable function on C, apart from one point, which is the pole at s equals 1, which is equivalent to the divergence of the harmonic series that you study in calculus. This analytic continuation was realized by means of what's called the integral representation of a zeta function. And this integral representation has the property that you can change variables on the limits of integration and use what's called the modular transformation law of a theta function. And this analytic continuation, therefore, then gives you a beautiful functional equation, namely that the values of the completed L function at S relates to the values at 1 minus S, provided that you take into account this multiplicative factor. This gamma of 1 minus S is a special value of the complex gamma function. And along the way, it turns out that because of the properties of this multiplicative factor, this function, the zeta function, has zeros. It vanishes at every negative even integer. So these are facts that Riemann was able to determine from his zeta function. Great. So why does all of this matter? Well, let me just give you a famous instance where this work of Riemann matters, and it allows me to talk about Ramanujan very briefly. So Ramanujan famously made the claim that you see here on the title of the slide. Under my theory, 1 plus 2 plus 3 plus 4, so on and so forth, equals negative 1/12. If I tell you this, you will at once point out to me the lunatic asylum, Ramanujan. This was a claim that Ramanujan made in his correspondence with Hardy before he traveled to England. It turns out that Hardy, as an analytic number theorist, would have recognized that this claim is not so crazy. And let me now use Riemann's idea to give some semblance of reasonableness, if that's a word, to this claim. So as I mentioned earlier, zeta of 2 is pi squared over 6. The sum of the reciprocals of the perfect squares add up to pi squared over 6. Now, Riemann's zeta function at -1, if we pretend is the series evaluated at -1. So remember, the series for the zeta function is defined here. If I let s equals -1, which I'm not allowed to do because this condition fails, but if I were allowed to do that, then I could say that zeta of -1 somehow represents the sum of the positive integers. And then we have the functional equation of Riemann relating zeta of -1 with zeta of 1 minus -1. But zeta of 1 minus -1 is zeta of 2, which is pi squared over 6. So if you substitute pi squared over 6 here and then multiply out all of these other factors, you'll be very happy to see that you actually get -1/12, exactly as Ramanujan claimed. All right.
Sorry to interrupt, Professor Ono.
Yes.
There's a question for the previous slide.
This one.
No,
this one.
No, the one before.
This one.
Yes. So someone is asking about point number 3. If you could explain it again.
So this is what's called the functional equation of the zeta function. If you want to evaluate the zeta function at, say, s equals -5, right? If s is -5, you can't use formula 1 because -5 is not greater than 1. But zeta at -5 can be evaluated because 1 minus a -5 is zeta of 6. And Euler gave a formula for that. So the functional equation is something like a log of trigonometry, right? Sine of theta is sine of theta plus 2 pi. Well, this is zeta of s is zeta of 1 minus s, but times this auxiliary factor. And that's how you would use this functional equation. Great. So let me show you a graph of the values of this function. Except I don't want to evaluate this function except only for complex numbers of the form 1/2 plus it. I here is a square root of -1, and t is a real number that will be chosen from the interval 0 up to 50. So if t equals 0, this is just zeta of 1/2, and zeta of 1/2 is around -1.46. So if you add to 1/2 multiples of I up to 50i and graph that with the computer, you'll get this beautiful curve. And on this beautiful curve, you will pass through the origin a number of times. And for every value of t where this curve crosses the origin, it will turn out to be a 0 of the zeta function. So you can do this on your computer. You can find these zeros. So let me just point this out. Zeta of 1/2 is -1.46 something or another. And as I mentioned, the first few zeros correspond to these first few intersections on this curve. And what Riemann conjectured is that all of the non-trivial zeros have to lie on this curve if you let it go on forever. In other words, if you were to replace this 1/2 by any other number, like 0.49, if you were to replace this 1/2 by 0.49 and added to 0.49 any multiple of I, the corresponding curve would never go through the origin. All of the zeros, apart from the negative evens, lie on the continuation of this flowery curve. And that is the Riemann hypothesis. Now, I haven't motivated to you why that matters. I will in the next couple of slides. So if you do this on a computer, or this can be done not just numerically, it can be done exactly. You need to use what's called complex analysis. And if you've had a course in complex analysis, you probably know about the residue theorem, or you know about like the argument principle, and formulas of this type allow you to locate zeros of meromorphic functions through residue calculus. Now, what Riemann said is that it would be very desirable to have a rigorous proof of this statement. All right, great. So why does this relate to counting prime numbers? All right, so I might be showing you here a theorem you don't know. If you don't know it, I'm glad to be telling it to you, because this is a theorem that you could discover on your own with the help of a computer. So let me read this theorem in backwards order. Let's define the Chebyshev psi function, psi of x, to be this expression. So psi of x means you sum up all the powers of the prime numbers you encounter up to x. So for every prime power you encounter up to x, add log p. So let's do an example. if x is 6, let's count from 1 to 6. If x is 6, 1 is not prime, don't add it. You get to 2. 2 is less than 6 and it is prime, add log 2. Then you get to 3. 3 is less than 6, so now you have log 2 plus log 3. Then from 2 to 3, you go to 4. 4 is 2 squared, so you add another log, a log 2. So that would be log 2 plus log 3 plus another log 2 when you get to 4. Then you get to 5, which is prime, and that doesn't exceed 6. 6 is composite, so there's nothing to do. So psi of 6 is just a number, log 2 plus log 3 plus log 2 plus log 5. So what the psi function is doing is it's keeping track as you count from 1 to x, and every time you encounter a prime power, it adds the logarithm of that prime base. So try to imagine a graph of this function psi of x. It's a stair-step function. It's horizontal until you encounter a prime power. It jumps by a log p, and it's horizontal for a while. And then when it encounters a prime power, it jumps, so on and so forth. One thing that you know for sure is that the prime squareds, the primes cubed, the large powers of primes are very, very rare. The primes are more common than the prime powers. And so this psi of x is, heuristically speaking, a characteristic function for the primes. It counts them, it locates them. And what Chebyshev and von Mangel proved is that Gauss's conjecture, which we call the prime number theorem today, Gauss's conjecture is equivalent to the assertion that the limit as x goes to infinity of psi of x over x is the number 1. All right. Now, if this isn't, let me show a picture which clarifies what I'm talking about. You yourself, with your computer, can compute psi of x and graph it. It's a stair-step function. If you graph the best linear interpolation for this stair-step function, you get this dashed line, this line that I've shown you here. All right. What you might not know, but what I will tell you is that the slope of this line is about 1. It's almost 1 on the nose. Of course, the y-intercept is not 1 because it takes a while before you get a prime, right? The first prime is at 2. So this function is at 0 for some time. And because of that little hiccup, you get this. But try to imagine what you're trying to do then if you're trying to locate primes. Wouldn't it be wonderful if you could prove that this blue stair-step function had to live between a function that lies above it and a function that lies below it that you could define? Because what would that mean? Wouldn't that mean that if there was a function below the line y equals x, that this stair-step function had to lie between? Wouldn't it tell you that you couldn't go too long without encountering a prime or a prime power? And that's exactly the idea of Chebyshev when he invented this function. So why does the Riemann hypothesis matter? The Riemann hypothesis is all about the goal of showing that this blue stair-step function, which is not differentiable, every time it counts a prime, you get one of these corners. The goal of Chebyshev is to show that this function psi of x is doing its very best to mirror this line with slope 1. So what does that have to do with the non-trivial zeros of the zeta function? And this is where it matters. It turns out that von Mangel, he proved this. You can write down an exact formula for psi of x. You can write down an exact formula for this non-differentiable but continuous function. What is it? It's x minus log 2 pi minus 1/2 log of 1 minus 1 over x squared. This lowercase x is meant to be a capital X. It's a typo. If this red stuff was not here, this would be a perfectly fine function and it would be differentiable and there'd be no corners. The only reason that this function has those corners and why it's allowable that we can study it by means of analysis is because the Riemann zeta function has infinitely many non-trivial zeros. Call them rho, and if you add them up, x to the rho over rho, that is the difference that's preventing psi of x from being this elementary function. If we want psi of x to be asymptotic to x, The name of the game is to show that these last three terms have very little size as x goes to infinity. Well, of course, log 2 pi is a number. It has basically no size as x goes to infinity. As x goes to infinity, 1 minus 1 over x squared rapidly tends to 0, and log of 1 is 0. So the only obstruction from psi of x being x as x goes to infinity is entirely captured by the generating function for the non-trivial zeros. They are exactly what prevents psi of x from being the target function in the prime number, in Chebyshev's theorem. So by the way, if you could prove that the real part of every one of these zeros is 1/2, which is the Riemann hypothesis, then the prime number theorem follows immediately. We know enough analysis to locate these zeros and how they are distributed, and that series is convergent. So the error term would be of order x to the half, and the square root of x in this sort of expression has no size compared to x, right? 1,000 versus a million, 1,000 is barely a blip. 10 to the 8th versus 10,000, 10,000 is barely a blip compared to 10 to the 8th. And it is in that spirit why knowing that the error term is small is related, gives the Riemann hypothesis and the prime number theorem, and the Riemann hypothesis guarantees that that error term is really quite small. Great, that's why the Riemann hypothesis matters. I have to say though, that Gauss's conjecture was proven without first proving the Riemann hypothesis, and that was a major triumph by Hadamard and de Vallée-Poussin. They were able to prove that pi of x is asymptotic to x over log x without knowing the Riemann hypothesis true. They were able to make use of the fact that the non-trivial zeros have real part less than 1. They don't have to exactly be 1/2, and they were smart enough to make that argument work. Now, that doesn't mean that the Riemann hypothesis doesn't matter. That just means that in an asymptotic, as x goes to infinity, we know how many prime numbers there are. But notice, if I really want to know how many prime numbers there are in any reasonable application, I'm not allowed to go to infinity. And in that regard, we are very far from knowing what the prime number theorem and combined with the Riemann hypothesis predicts. So why does the Riemann hypothesis matter? It matters because if it is true for all x after 2,657, the difference between pi of x and li of x, the logarithmic integral, is explicitly bounded by square root of x log x over 8 pi. If x is a million, this is very small, right? And so it'll tell you that this special function li of x is doing a remarkable job of predicting for you how many primes there are. Good. So if the Riemann hypothesis is true, we have very tight information. If the Riemann hypothesis and its generalization, called the generalized Riemann hypothesis, are true, there are many more applications of this type. So basically every deep question on primes would be solved if we know the Riemann hypothesis. That's not quite true. The Riemann hypothesis does not imply the twin prime problem, but it implies basically everything else. If you're interested in the study of what are called elliptic curves and class groups in algebraic number theory, we are very far from knowing how they behave on average. And so most of the best state-of-the-art theorems still rely on assuming the Riemann hypothesis. Elliptic curves play a prominent role in the internet, the theory of the internet, and in signal processing and cryptography. If you're interested in lattices and quadratic forms, low dimensional quadratic forms, in particular dimension 3, we know very little without assuming the Riemann hypothesis. And believe it or not, even studying the symmetric group as you would in a first course in abstract algebra have the properties that we don't really know their properties without knowing the Riemann hypothesis. Let me give you an example. If I gave you a symmetric group Sn and I asked you to find or bound the largest order of the elements in Sn, how would you do it? Well, this is very hard, right? The order of an element is the least common multiple of each of the cycle lengths in a permutation. So that's a theoretical statement, but how do you get strong upper bounds for these orders unless you know how the primes are allowed to be among the factors of these cycle types? So there's no escaping the need for knowing where the prime numbers are. For primality tests and algorithms that are number theoretic based, the running times of these algorithms almost always assume the Riemann hypothesis. Quite literally, you can go to MathSciNet and count how many papers assume the truth of the Riemann hypothesis or the generalized Riemann hypothesis, and the count is into the thousands. Let me give you one very beautiful, explicit example of where the Riemann hypothesis rears its very strange, insidious claws on an elementary to state problem. It allows me to tell you about Ramanujan again. And one of Ramanujan's many important works that he wrote in England was on quadratic forms. He famously understood quadratic forms in 4 variables, and he wished to understand quadratic forms in 3 variables, say x, y, and z. And he made very little progress on them because to this day, we have made very little progress on them. It's difficult. So there's a quadratic form called Ramanujan's ternary quadratic form. And this quadratic form appears in his paper in this quote. Ramanujan says that the even numbers which are not of the form x squared plus y squared plus 10z squared are the numbers of the form 4 to the lambda times 16 mu plus 6. Okay, that's easy. Any even number that's not a power of 4 times an integer that's 6 mod 16 are represented by this form. Namely, you can find an integer x, y, and z, such that this form gives that value. What Ramanujan was interested in is how come the odd numbers have no obvious law? Ramanujan says, while the odd numbers that are not of this form, x squared plus y squared plus 10z squared, and then he offers a list of numbers, do not seem to obey any simple law. So of course, the simple law cannot be 79 is on this list because I cannot find x, y, and z that makes 79 out of x squared plus y squared plus 10z squared. That's not what he's saying. All right. So a number of years ago, together with my friend Soundarajan, who is Indian by birth, he grew up in outside of Chennai. In 1997, we wrote the following theorem. Assuming the generalized Riemann hypothesis, the only positive odds not of Ramanujan's form are listed here. The only ones, meaning the last odd number that is missed by this quadratic form is 2,719. I was so disappointed when we first proved this theorem. I was hoping that it would be 1,729. Wouldn't it be amazing if 1729 was the last odd number missed by Ramanujan's ternary quadratic form? But never mind that. If you want to see 1729, it's on my t-shirt. The taxi cab number is here, but it's also here on this slide if we permute the digits to get 2,719. 2,719, subject to the Riemann hypothesis, is the last odd number that you cannot get by substituting in integers for x, y, and z. So you might ask, what does we mean there is no simple law? Well, a number of years ago, I asked one of my PhD students, Lemke Oliver, to try to prove the converse. If you have an odd number larger than 2,719 that is not of this form, can you prove that the Riemann hypothesis is false? And he basically did this. He proved a theorem that said if n is an odd integer greater than 10 to the 15th that is not of the form x squared plus y squared plus 10z squared, then he produced a neighborhood in the complex plane that did not intersect with the real part of s equals a half that he could prove had to have a 0. And so what was Ramanujan's claim? Ramanujan's claim is that the odd numbers that are not of this form do not seem to obey any simple law. Well, I now know what that law is, and it's called the Riemann hypothesis. So there's a lot of evidence for the Riemann hypothesis. People have computed zeros with a computer. No counterexamples have been found. Many people have tried to show that a proportion of the zeros satisfy the Riemann hypothesis, and they've done that. People like Selberg and Levinson, going back to the 1950s, were able to show that about 40%, at least 40% of the zeros have to satisfy the Riemann hypothesis, namely the real part is a half. People continue to work on this to this day, but as you can see, it must be very hard because in the span of half a century, we went from at least 40% to at least 41%, right? So it's very technical. People like Hadamard, de Vallée-Poussin, Vinogradov, and others actually found explicit regions of the complex plane which cannot have a zero. The regions that are colored here in blue are not allowed to have a zero of the Riemann hypothesis, a Riemann zeta function. All the zeros are conjectured to be on this line, so it's not very pleasing to see that this white bubble here in the middle that tends to infinity as a tube are possible locations for zeros, so we're not doing very well. What about prospects for a proof? Well, there's many arguments that people have and programs that people have set forth, hoping to be the beginning of a program that could lead to a proof. And so far, none of that seems to be working out very well. This is a nasty, difficult problem. So to close, let me just tell you a little bit about some work that I did with my friend Don Zagier and some of my collaborators on one of these programs, the programs of the random matrices. So this program was initiated by Freeman Dyson, Hugh Montgomery, and Andrew Olidzko. And they studied the zeros, the non-trivial zeros of the zeta function from a statistical perspective. And based on some heuristics and based on quite volumes of calculations, they concluded that the zeros of the zeta function suitably normalized should behave like the eigenvalues of random large Hermitian matrices. I don't want to get into that to explain what all of that means, but there are statistical models that the zeros of the zeta function seems to mirror with astounding accuracy. Because of that, my friend Don Zagier and I decided that maybe we should revisit some of the programs that were set forth with the aim of proving that the Riemann hypothesis. And the one that we wanted to study is called the Polya-Jensen program. This is the famous Polya, who was a longtime professor at Stanford. And Jensen is the famous Jensen that you learn about in analysis of, say, Jensen's inequality. Jensen and Polya recognized that they could identify a robust criterion that is equivalent to the Riemann hypothesis. And this criterion makes use of a doubly infinite family of polynomials. So if A is a real sequence, A of n, so it's an arithmetic function that takes real values, then what Polya and Jensen understood was that they could come up with a doubly infinite family of polynomials called the Jensen polynomials, indexed by D and N. D will stand for the degree of the polynomial, and N will stand for its shift. So what did they write down? This polynomial is a tweaking of the ordinary binomial expansion, except if you take the polynomial x plus 1 to the d, you then insert the values of A of n in this way. The constant term you replace by A of n. The coefficient of x you replace by d times A of n plus 1, so on and so forth. You take the binomial expansion for x plus 1 to the d, and then start inserting in order, beginning at the constant term, the values of the sequence A with shift n, meaning starting at A of n. And they found that they could come up with a criterion that's equivalent to the Riemann hypothesis using such polynomials. A polynomial of real coefficients is called hyperbolic if all of its roots are real. And the Jensen-Polya theorem is as follows. If you define gamma of n to be the Taylor coefficients of what's called this renormalized Riemann xi function, then the Riemann hypothesis is equivalent to the hyperbolicity of this doubly infinite family of polynomials. if you compute the Taylor coefficients and get one of these polynomials and finds that one of them has a pair of complex conjugate roots, either your program is wrong or the Riemann hypothesis is wrong. I regret to say, I think your program would be wrong. What was known about this? Well, for shift 0 and all degrees up to 2 times 10 to the 17th, Schaas proved that all of these polynomials are hyperbolic, all meaning only real roots. That's a finite set. The only infinite set before I work correspond to the degrees up to 3. For every n, for degrees up to 3, work by Sordis and Norfolk and Varga and Dimitris and Lukas prove the hyperbolicity of these polynomials. Degree 1 is rather silly because the Taylor coefficients are real and every linear real polynomial has real zeros. For degree 2 and 3, we have several advantages working for us. But for degrees larger than 4, honestly, nothing was known. And the Riemann hypothesis is equivalent to the assertion that for all choices of d of n and n, these polynomials are hyperbolic. Well, what did we prove? We proved that there is a way to renormalize these Jensen polynomials so that for fixed d, as n goes to infinity, these polynomials converge to what are called the Hermite polynomials, which are well known to satisfy the random matrix model and also well known to have the property that all of the roots are real. So what did we do? Before, nothing was known for every d up to 4, greater than 4. Our theorem now is for every degree d. All but possibly finitely many n have the property these polynomials are hyperbolic. We now know that for all degrees up to 10 to the 20th, not just 3, for all degrees up to 10 to the 20th and all n, these polynomials are all hyperbolic. Why do people care about this theorem? Well, this theorem offers very good evidence for the Riemann hypothesis. And if you're interested in random matrix model distributions of zeros, well, because the Hermite polynomials automatically satisfy GUE, our theorem proves that the Riemann zeta function satisfies GUE in a derivative aspect. If you are allowed to take a few derivatives of the zeta function, then the derivatives of the zeta function have zeros, which tend to behave like random eigenvalues of Hermitian matrices. And that's that. Why does the Riemann hypothesis matter? It matters because it's related to the problem of the primes and underscores so much of modern mathematics. Are we close to proving it? No, but certainly recent works have shed light on how to think about the Riemann hypothesis. And with that, let me see if there are any questions.
Thank you so much for the very nice talk. There are several questions actually. And let me just call one by one, and then the person who has asked a question, you can probably unmute and ask yourself. So the first question is from Angad Singh. Angad, if you can unmute and ask your question.
Hello, good evening, sir.
Good evening.
Sir, how are you, sir?
I'm fine. How are you?
I'm also good, sir. Sir, there was a question related to Riemann hypothesis, sir.
Yes.
Sir, if all the mathematicians have done a lot of work on Riemann hypothesis, so do we require an entirely new branch of mathematics to solve it?
Maybe. That may be true. Yes.
So because I was also thinking of going to pursue the same line, whether there exists a new branch of mathematics or not, sir. Just for proving this problem.
Yeah, that's a very bold idea. If I knew how to do it, I would myself. So this will take it'll probably take incredible ingenuity and creativity, I think, to solve this problem. I don't think that all the mathematicians that have been thinking about it have missed a natural approach.
Yes, sir. And one more question, sir. Sir,
Yes.
if we prove Riemann hypothesis, then will we be able to control the primes? We will be able to know the nth prime and the exact value of pi x.
Well, not exactly, but very precisely.
All right, sir.
Yeah, very precisely, but not the exact values.
All right, sir. Thank you, sir.
Sure, sure.
There is a question from Professor B.V. Rao. Professor Rao, if you can unmute and ask the question.
Yeah, thank you. Professor Ono,
Yes.
I have questions. Number one, do you think that probability will play a major role if and when the Riemann hypothesis is decided? And the second question is, you said, according to your theorem, for every D, there is a D star, so that for n larger than D star, these polynomials are hyperbolic.
That's right.
How does D star increase as
Very good. Yeah, excellent question. So the first question is probability, about the role of probability in studying the distribution of primes and the like. Very much so. Probabilistic arguments are often the heuristics that we try to develop into proofs in analytic number theory. So the interplay between probabilistic ideas and analytic number theory, it's almost always just slightly below the surface. There are very few theorems, I'd say, that are proven in this kind of mathematics that don't have the property that we're able to make a good conjecture about the behavior, only discover later that the conjecture wasn't quite right. And that's because of the very strong role that probability has played in successfully allowing us to form conjectures. Your next question is very good. So you say for each D, we produce a D star such that the polynomial JDN is hyperbolic if n is bigger than D star. There's two parts to that. As D, so that D star grows like e to the 8D over 9. E to the 8D over 9. It grows very rapidly, okay? However, for small d, for d up to 10 to the 20th, we have some tricks. Namely, we know the low-lying zeros of the zeta function that have already been pre-computed, and using that for d up to 10 to the 20, we're able to show that d star is 0. Okay.
Okay.
Good question. Very good question. I'd like to show that D star is, if I could show that D star grows very, very, very slowly compared to D, there would be a chance for proving the Riemann hypothesis using other arguments. But because that grows so rapidly, we lose control.
Yeah, let me just ask, so is there any theorem in that direction? If the D star has, for example, quadratic growth,
yeah,
then this is true.
Yes, but those are my secret notes. Yeah, but it has to be much better than D squared. Quadratic growth is still bad. Yeah. Yes.
Okay.
No, but yeah. Your question is very much along the lines that I spent the whole year last year thinking about.
Okay. Let me just ask a final question.
Yeah.
You said your student proved that if there is an odd number which is not of that form,
Yes.
then a large odd number, there is a 0 of the zeta function away from the line, right?
That's right.
Okay, would you please be kind enough to tell me the reference? I do not know this area.
Yeah, I don't actually have that here on my laptop, but the name is Robert Lemke Oliver, Lemke, last name Oliver, Oliver. And if you go to his website at Tufts University, you will probably find it.
Thank you so much.
Sure.
Thank you so much.
Yeah.
The next question is from Bharat BR. So Bharat, if you can unmute.
Hello, Professor.
Hello, how are you?
I'm fine. So, how are you doing?
I'm very good.
So, you had stated several applications of Riemann hypothesis in the area of pure mathematics.
Yes.
So, if there are any, what are the applications of the Riemann hypothesis if it is proven to be true in the area of applied mathematics, Professor?
Right. Well, so some of the areas that I was discussing are related to like running time algorithms for, you know, in primality testing, factorization algorithms. Other algorithms that come into play would be group theoretic algorithms if you're using the permutation groups, right? If you want to know that certain calculations in permutation groups don't take too long, the Riemann hypothesis will help you.
Okay, thank you very much, Professor.
Sure.
The next question is from Shomavo. So he's asking about Ramanujan's ternary quadratic form.
Okay.
Instead of 10, if you replace it with other numbers, are there similar results?
Oh, well, of course, except the results tend to become more complicated. 10 is sufficiently small that the quadratic form isn't easily understood, and it's also is sufficiently large so that the representation theory for it is not as simple as what Gauss tended to do, but it's sufficiently small so that you can work out the exact relationship with L functions to get statements about the zeros and the determination of integers which are missed. In principle, for every ternary quadratic form, the process will work, okay? But it could be that the number of L functions that you have to study grows with the coefficients. But in principle, the theory is the same.
The next question is from Shubham. Shubham is asking, what does 41% of infinitely many zeros mean mathematically?
Good question. So we have known for quite some time how many zeros of the zeta function have imaginary part up to a large number x, right? So suppose you consider the upper half of the complex plane and consider complex numbers with imaginary part positive, but no bigger than x. So it's like the upper half plane, but you draw a vertical barrier at the top at some large number x. So we know with very tight asymptotics, the number of zeros of the zeta function in that region. We want them all to lie on the line real part of s equals a half. So if you were to count the number of zeros on real part of s equals a half up to x divided by the number, you get a percentage. And if you let x goes to infinity, these percentages vary. But when we say at least 41%, it means x goes to infinity, those percentages.
Sorry, Professor, you were muted by mistake.
Oh, it says that if you count the percentage of zeros up to x that satisfy the Riemann hypothesis, that's a proportion you can compute for each x. But if you let x goes to infinity and can prove that from some point on, the percentage never dips below 41%, then you say the number of zeros is at least 41% in favor of the Riemann hypothesis.
The next question is from Kaushik Bora. Kaushik, if you can unmute and ask the question directly.
Hi, Professor. Hi, good morning. I think I can say good morning. I'm probably the same time zone right now. Yeah, I'm in Kentucky. Okay, so I'm a physics graduate student by training. So my question has a little different flavor probably. So in recent time, it seems like some mathematical physicist has attacked this problem like with some Hamiltonian approach. So like, I just want to know if you can say a few words about it, like how seriously mathematicians do take this approach.
Wow. Well, so without singling out one approach versus another, let me say that each approach that people are working on are favored by the people that happen to work on them. And so, you know, I don't know many people who are trying to work on more than one approach at a time. And so I think it's fair to say that right now the mathematicians and the physicists in this regard are probably not collaborating.
Okay. Okay.
But make no mistake, I don't think anyone is ahead of anyone else, because I think we're all very far away from approved.
Okay. Okay. Okay.
Professor
Okay.
Ono, do you still have time for a few more questions?
Maybe 2 or 3 more, because then I need to take a break before my 9:30 class. Sure.
The next question is from Gorango. Gorango, if you can unmute and ask directly.
Good morning, sir.
Good morning.
It was an amazing talk, first of all, and I'm very
Oh,
glad
thank you.
to attend. So my question was a little not mathematical. John Nash was a little, he was he was working on the Riemann hypothesis by reading E.T. Bell's Man of Mathematics at an early age. So is there any contributions from John Nash that that helped?
That help with the Riemann hypothesis. I knew John Nash when I was a postdoc at Princeton. He was still alive. It was in the mid 1990s, and he came to seminar. And I have to say, we were always wondering what he was thinking. And a few times he sent me a number of emails. But in terms of anything explicit or concrete in connection to the Riemann hypothesis, there's nothing that I'm aware of in his work that that represents a major contribution. But that doesn't mean that maybe he had written down somewhere something that we would like to know. I don't know.
Okay, so in case of Ramanujan,
In other words, the question you're asking, we were all asking at the same time. Like Peter Sarnak and I, we discussed this many times. John Nash is in seminar. Wonder what he's thinking. But he'd sit in the back, wouldn't say anything to anyone, and then disappear. Yeah.
okay,
He was a ghost.
okay. Okay, so my another question will be on pertaining to Ramanujan. So apart from those quadratic things that you mentioned in the slides, what are the other contributions from Ramanujan in the Riemann hypothesis?
Oh, to the Riemann hypothesis.
Yeah.
Well, to be perfectly fair, I don't know, and I'm not sure that Ramanujan connected the ternary quadratic form to the Riemann hypothesis. I think he was looking for that law, and he wasn't quite sure what it was. I think it's closer to say that earlier on in Ramanujan's career, he got tripped up by not understanding the significance of the zeros of the zeta function. So he famously had a proof of the prime number theorem as if the Chebyshev psi function was a continuously differentiable function, which is not allowed to be. And so I don't think this was an area in which Ramanujan made an important contribution.
Okay, sir. Thank you,
Yeah,
sir.
Ramanujan's skills were very different, right? Ramanujan wasn't aiming to prove someone else's major conjectures. It is true, early in his career, he wanted to prove the prime number theorem, but we really remember him for the contributions that he made that were of his own origin and his own creation, right? That's where his powers were.
Okay, thank you, sir.
I have a lot of questions actually, but in the interest of time, I'll just ask 2 more to Professor Ono very quickly. So one question was, is there any equivalent reformulation?
I'm sorry, is there equivalent reformulation of what? All right, I can't hear you.
Sorry. So is there a reformulation of Riemann hypothesis in terms of modular forms?
Well, there are Riemann hypotheses for L functions of modular forms. So the Riemann hypothesis now is used in many settings. So if you ask about Riemann hypothesis or Ramanujan conjecture, so on and so forth, there are statements that you might see that don't resemble anything like the original Riemann hypothesis. But if you were to take some courses, you'll see how mathematicians were led one step after another to obtain analogies and generalizations. So in that regard, yes, right? There's a famous conjecture of Ramanujan on the size of the values of his tau function, which can be reformulated in terms of zeta functions of algebraic varieties. And that's what Andre Weil did. And that's now often referred to as a Riemann hypothesis. And so one of the famous Riemann hypotheses, which has been proven, is that the zeros of local L functions for modular forms satisfy the correct norm condition. But it's a different kind of L function and has its different kind of applications.
One final question which we ask all our speakers. If you could suggest some good books or sources to get into this area or to read about Riemann hypothesis.
Oh, gee, yeah. I don't know where to start. Depending on your background, if you are just starting out as a student, one of my favorite books is by Hardy and Wright on number theory. It's a paperback published by Oxford. It's a very good one. E.M. Wright and G.H. Hardy's book published by Oxford on number theory. And then moving on from there, as a graduate student, you might want to pick up Harold Davenport's book called Multiplicative Number Theory. And then from there, you might want to consider this book by Ivaniech and Kowalski. Maybe, and then already by looking at these books, you'll be introduced in the references to other standard books. So the book by Hardy and Wright, that's the first one. The book by Davenport called Multiplicative Number Theory would be the second one. And then by that time, you're probably a beginning graduate student, if not already a graduate student, and you'd be reading a book by Ivaniech and Kowalski.
Thank you
Very
so
good.
much, Professor Ono.
My pleasure.
There are still more questions, but I apologize to the people.
Yeah, I need to take a short break, and my graduate class starts in 8 minutes, so I really have to take that.
But I hope that we'll have another meeting with Professor Ono in the future, and then we could discuss more. So thank you so much, Professor Ono, for the
All right, thank you very much, everybody. Okay, bye-bye. Have a good day.
Bye.